Okay, so the first thing we did was volume by slicing. And with volume by slicing, we had to figure out what the area was that we were going to move across a certain distance. So we ended up with volume is equal to the integral from A to B. We had to find what the area was. If it were squares, we figured out that it was length times width. If it was a triangle, they could be semi-half circles. We just need to find out what the area is, okay? Then the second thing we did was volume by disk method. And volumes by disk required us to take a region and rotate it about the X or Y axis. So we took a region R. I shouldn't say R. We took a region and rotated it about the X or Y axis. So if we had a region that looked like this, and this was our curve, and it was inside this region, and so this was my region. And so this was C and this is D. And actually, I'm going to chop a little bit of this off. Okay. Oh, nope. I have to make it go all the way to the edge because we don't know how to do that yet. So let's make it go all the way to the edge. We're going to make it go all the way to the edge. Okay. So this is my region and I revolved it. So let me copy this picture real quick because I'm going to need it again. And I went to too much to figure it out. Okay, no, nope, you're not listening. I said do the whole thing. Do the whole, come on, Lasso, do the whole thing. Thank you. Okay, so we said if we're rotating this region about the x-axis or some line horizontally, that means if it's rotating this direction, that means I should see discs in that direction. I find the radius of my disc, which is this height. So that's y is equal to some f of x. We got to find what that radius is. So when you find your radius, then you get the volume is the integral from wherever you start to end of pi times the radius squared dx. Now, if I have to rotate about this direction, I don't want that to be green. If I'm rotating this way about the y-axis, then now I should see discs in that direction. So now this is x is equal to g of y. I need to identify the radius. And then my volume will be the integral from C to D of pi. This times my radius is a function of y. Okay, so that's what we've done so far. So now what we're going to do today is called volume. We're going to use the washer method. So volume by washers. So a washer is technically something that looks like that. Let me make it look more like a circle. Okay. And then there's another circle inside of it. Kind of like a donut. All right. So this is a washer. If you've ever had to change the tire on your bike and you use the screw, you have that little round metal thing that helps you to keep it from grinding as it's turning. Or if you have if you've changed the sink, the faucet in the sink, you'll see a little metal thing. That's a washer, otherwise known as a donut. Okay, so I only care about this area inside here. Okay. So I need to find the area inside of this thing. All right, so here's my area that I'm worried about. So remember, anytime we're doing these, we need to identify the area. So in the previous problem, the area was the area of a circle. Okay, so now this one's actually rather easy. Okay, here is the radius of the big circle. Okay, and here is the radius of the little circle. When it gets to be where I want it to be. Okay, so that's the radius of the little circle. Okay, so how can I find the area of the green region? So I'm going to call this radius big R, and I'm going to call this radius little r. So how can I find the area of the green region?
Find both areas and subtract the little one.
Okay, find both areas and subtract the little one. Okay, so what's the area of the big circle? Gustavo?
Give you in the form of a formula.
Oh yeah, I want a formula.
Is it pi r squared?
Okay, so it's pi times the big radius squared. And the area of the small circle that's just pi times the little radius squared. So therefore, the area of the green region okay, it's stuck for a moment. So the area is equal to the big radius, the big area squared, the big area, so pi times r squared minus pi times little r squared. So therefore the big area is equal to pi times the big radius squared minus the little radius squared. Okay, so now we found the area of a washer. Okay, so now if that's the cross-sectional area of our solid, then that's what we're going to have to use. Okay, so here's the problem. I have so I'm going to have two functions. This is y is equal to f of x. And then I have another function. And this is y is equal to g of x. And so the region inside is what I'm concerned about. So here is my region. So now I'm going to revolve this thing about the x-axis. So when I revolve it about the x-axis, I get something that looks like this. And then I get something that looks like this. So when I revolve it about the x-axis, I can choose any point x that I want. And the point on this curve is going to revolve around the x-axis and give me a disk. But the point also on this curve is going to revolve around the x-axis and give me a disk. Okay, do you see the washer? Okay, so there is a washer. So basically what this thing is going to be is this is going to be some three-dimensional shape. That has a hole in it. That's bad. Yeah. So this thing can hold water. So washers hold water. So if you draw your circles and you see that you have a washer, it can hold water, then you will use the washer method. So notice I didn't get a disc like up here. Up here, I got a full disc. And that was it. I just got the one disc. Or I got the one disc. But now I have two functions, or maybe just one function. It depends on the problem. But when I revolve it, I get two circles. And so the thing that's going to be solid, so that kind of looks like a bowl that goes out like that and then comes in like this. So it comes in, whoop, and it goes out. And that whole thing is solid and it can hold water. Okay, so now what's the area of that thing? Well, this is my X. I'll make that black because it's awfully small. Whoa. When that happens. Okay, so this is an X. So now this is the small radius. So let's do the big radius first. So the big radius in this problem is the F, And the little radius in this problem is the G. So my formula is going to be volume is going to be the integral from A to B of pi. You have to determine what the big radius is, and you have to determine what the little radius is. And that is the washer method. Okay. Okay. So consider the plane region bounded by the curves. The first curve is going to be y squared equals x. And the second curve is going to be y is equal to x cubed. So they kind of look like what I just drew. Okay, so x is equal to y squared is that first one. So here we go. So this is almost that exact same example I just did. So x is equal to y squared is a parabola. So it looks like this. And y is equal to x cubed is a cubic. It looks like this. So this is y is equal to x cubed. And this one is, well, it's actually, I'm gonna fix it. It becomes y is equal to the square root of x because I need everything in terms of x for this problem. Okay, I gotta. Okay. All right, so now I'm going to revolve this about the x-axis. So when it says revolve about the x-axis, just draw your little thing so you know which way you're going. So that means I'm now going to choose. So I already know when I revolve it about the x-axis, the thing is going to have this shape. And this is going to have this shape. Trying to do here. Okay, so for any particular x I choose, I go up to the first curve and I revolve around, I get a circle. So I can now see that the radius of the small function is what? What is the radius of the small function?
Will the radius be x to the 3?
Okay, so that's going to be x cubed. Okay, so I need an honest answer as to anyone who was not sure how to find that, because I will explain it if you're honest with me and tell me you didn't know how to figure that out.
Can you explain it one more time, please?
Okay. All right, so let's go here. I'm just going to go to the side for a moment. Let's take for a second the curve y is equal to x squared. So if I'm at 1, what is the height of this function? What is that value?
You said at the height.
Yep. What is this?
Isn't it just 1?
Okay, who said that?
Q.
Okay, so I think that's why some people are confused. Okay, that is correct. So the value, the y value, the x value is 1. The y value, which is the height or the distance it goes up, is also 1. Okay. If I choose the value 2 and I go up here and I scroll over to here, what is this height?
4.
4. Okay, so if I'm at 2 and I go up to this value, the value on that curve, you took 2 and you squared it. So you got 4. Now let's choose an arbitrary value. I don't know what it is. This is x, and I go up to the curve. How high is that distance?
X squared.
It is x squared. Because that's the value it would have on the curve. So let's go back over to this picture now. So I chose an arbitrary x and I went up to this curve. So I'm on the curve, y is equal to x cubed. So this height, which is my radius, is x cubed. Who I forget, was that Dizere, was it you that didn't understand it?
Yes, I understand now.
You understand now?
Yes.
Doesn't it feel better?
Yes.
Oh God, yes. Okay, so now Dizere, I'm gonna ask you, if I take that same x and I go all the way up to this point, I know my line's not straight, but I go up to this point now, what is that distance?
Would that still be x cubed?
Which curve is it on?
It's on the y square root of x.
So what's its distance? What's the length?
Y square root of x.
Square root of x. Good. So what's the big radius?
Square root of x.
All right, I feel some sunshine. Okay, so now we can do the problem. Now we know what the big radius is. We know what the little radius is. So the volume is the integral. Well, we start at 0, obviously. What we don't know right now is what this value is. We don't know how far to go. So we already know we're going from 0 to something. We got to figure out how far to go. So we know we have pi. The little radius, the big radius is the square root of x. And the little radius is x cubed. So the only way to figure out where they meet is to set them equal. So you have to set x cubed, y equal to x cubed, equal to the square root of x. And so you get the square x to the 1/2 minus x cubed is equal to 0. So factor out x to the 1/2. That leaves you 1 minus x to the 5/2 is equal to 0. And you can see that this is x is only equal to 0 and 1. So this little bugger right here is a 1. Okay, so now this becomes the volume is equal to the integral from 0 to 1. I could pull the pi out, so let me pull the pi out. Integral from 0 to 1. Now I just get x minus x to the 6 dx. Okay, I integrate that real easy. That's pi. And then I get 1/2 x squared minus 1/7 x to the 7. Evaluate between 0 and 1. And my answer is 5 pi over 14. Okay. Okay. Any questions?
Yes, could you, so when you're finding the integral of that, and you're using the fundamental of a theorem of calculus, do you use the fundamental theorem of calculus independent of pi, or do you multiply what you get for that times pi?
It's independent of pi. Pi is just a coefficient. So so I can pull pi out and multiply by pi at the end, as if it were a 2 or another number. Yes.
So in finding the integral of this, you need to use the fundamental theorem of calculus of the stuff in the brackets, and then after finding that, you multiply that by pi.
Yes. So the fundamental theorem of calculus was used here because I found the most general antiderivative. Whatever that is, f of x, and then I evaluate it between a and b. So that will give me big F of b minus big F of a. Most general antiderivative.
Okay.
Okay, any questions? Okay. Revolve the same region about the y-axis and compute the volume. Okay, let's draw a picture. Now, I'm already going to tell you that this is going to be the volume is going to be the integral from C to D of pi. Now, this has to be a function of y squared. So I'm going to get the same curve. The same curve was x is equal to y squared. So that one's already perfect because this one was y squared is equal to x. So I already know what x is. So that function is x. Now the one I have to work with is this one, because this one is y is equal to x cubed. So I have to fix that one. I can't use y is equal to x cubed. So for the red one, I'm going to use x is equal to y squared. And for the blue one, I'm going to use x is equal to the cube root of y, or y to the 1/3. Same function, but written in terms of x, not y, because I am going like this. Okay. So therefore now we're going to get this curve to come back over here like this. And then I'm going to get the red curve to go up like that. Okay, here's my region. Okay, so this is the region. So I'm going in the other direction. So this time I'm going to choose a Y. Doop, 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 doop. So this time, since I'm going in the revolving around the Y axis, I'm going to choose a Y. I'm going to go up to the first curve and then draw a disc. And now I need its radius. So how long is that? If this is Y, then how long is that black line? It's the exact same way we did it before. So this is the little radius.
It's
Y squared.
Yes. Perfect. Okay. So now I'm going to take that same point. I'm going to draw a circle. Okay, same thing. Now I have to find this radius. So I go all the way up to the big curve. It lands right here. So what is the big radius?
Y to the 1/3.
Y to the 1/3. Oh my goodness. I am having a good day. Okay. And so we already know that this point from the first problem was 1. So if Y is 1 and if X is 1 and Y is X cubed, I know that this is also 1. So again, I'm going from 0 to 1 of pi. My big radius is Y to the 1/3. I'm going to square that. And I'm going to subtract off the little radius, which is Y squared. And I'm going to square that dy. And so now I get the volume, the integral from 0 to 1 of pi. Oh, I can take the pi out. Let's just pop it out. Times the integral from 0 to 1. I get Y to the 2/3. Minus Y to the 4th dy. And that comes out to be 2 pi over 5. Okay. All right, let's try another one. How are y'all feeling?
Good.
Starting to feel a little bit better. I hope so. I truly believe drawing the pictures helps. In fact, I wouldn't know how to do it without drawing the picture. Okay, so we want to find the volume of the solid generated by revolving the x-axis revolving about the x-axis, I apologize. The region bounded by the parabola y is equal to x squared plus 1, and the line y is equal to x plus 3. Okay. So the parabola is y is equal to x squared plus 1. And then I have a line, y is equal to x plus 3. Okay. So I'm going to draw this thing. I'm going to let you guys draw it first. So take a moment and try to draw this. Both of these are rather easy functions, so they're not hard to draw. And if you're not quite sure, just look on your quick study for calculus and answers, and it should be a picture of hopefully y is equal to x squared, I believe is on there. And the line y is equal to x plus 3. So I am giving you a few moments to graph this yourself. Okay, anybody want to hold their picture up to the camera? That'll be nice. I'd like to see that. Okay,
Yes.
Eric, can you push it up in the air a little bit more?
Yeah, like, see, like it's like towards the bottom of the paper. You
At the
see it?
bottom, keep it going. Push it up a little bit more. Okay,
see
I
it?
see your parabola. I think that's the first one.
Yeah.
You got to push it up a little bit more. Up in the air. I can't see the bottom picture.
Um. Can you not see it? It's okay if you guys see it.
Okay, anybody else? I think I'm looking to see if anybody else is holding their picture up to the camera. Okay, Juan.
Would it be something like this?
Okay, hold on. I'm going back to you. Where'd you go? Where'd you go? Yes. That is correct. Thank you, Juan. That looks beautiful. Okay. So if you didn't catch Juan's picture, he drew a parabola that wasn't as rickety as mine. You ever wonder why old people shake? You'll find out when you turn 50. Okay. And then he drew this line going through so he got something like that. All righty. I'm going to I don't want my region to be that big. There we go. That's better. Okay, much better. All right, so there's my region. I'm going to revolve this thing about the x-axis. So draw what that looks like. Oh, and actually it shouldn't, it's x plus 1, so it shouldn't be touching. it should be like that. Now it's right. Okay. Shouldn't have been touching. So revolve that about the x-axis. I hope you are working and thinking and not trying to wait for the answer. Okay. So you should have just picked that thing up and taken and done this. So you got this little piece going down like that. Maybe a little higher. No, maybe a little lower. Yeah. Okay. And then your red piece should be going like this. Okay, so mine is not the best, but it's the best that I can do at this moment. All right, so therefore, now what are you going to do?
We're gonna make circles around the x-axis.
Okay, so we're going to choose an X, find its value and make a circle. Find its radius. And call that little r. So what is little r of X?
X squared plus 1.
X squared plus 1. Okay, you want to take this big one. Well, guess what? I see a washer. And now that I see a washer, I need the big radius for that. And what is the big radius?
X squared plus 1.
Okay, what curve is it on?
Oh, x plus 1.
X plus 3.
X plus 3.
Okay. All righty, so the volume, the integral from up, we don't know where to go. Okay, we got to find these. We did the hard part. Now we got to find those limits. Okay, so this is pi. I know I'm going to have x plus 3 squared because that's the big radius. And I'm going to subtract off the little radius, which is x squared plus 1 squared dx. So I need to find my limits. I don't know where to start. So I'm going to start somewhere over here. I don't know this value. And I'm going to end somewhere over here. And I don't know this value. So I don't know those values. So we got to find those. Okay, so how do I find them?
Well, for stars, I think when it comes to the big radius, I think since if it looks like it's going to be 1 based on the position on the graph. So as I see these 2 2s, x-axis. So I think,
Okay, so we can't go how my picture looks or your picture looks. We have to find a mathematically sound reason that's going to give me my limits of integration. So what do I know about the 2 curves right here?
Is the bottom number 3?
Is the bottom number, did you say 3?
3, yeah.
Okay,
So this is how I would go. I would think of it like wherever the washer points are at. You get what I'm saying? So like,
okay, so we can't go by that either, but that
No.
is a very good, that's a very good observation when you're looking at it. But look, what do I know about the 2 curves at those 2 points?
Would we set them equal to each other?
Exactly. Okay, so at those points, the 2 curves are equal. Do you see that? So set them equal to each other and tell me what the x's are.
Well, if you're asking for the x's, I'm gonna say that the x is 1.
You said 1.
Mm-hmm.
Okay, you have to tell me how you solved it. Did it- Go ahead.
I honestly just looked at the graph.
Oh, you can't go by, my graph could be all kinds of directions. You can't look at my graph. You got to solve it.
You gotta move all the x terms to one side.
Okay, so you get x squared plus 1, whoops, is equal to x plus 3. Okay, what do I do next? Keep going.
Move x to the left and 1 to the right. And then set
Okay,
to
I was
0.
with you till you moved that to the other side. I want to move the 3 to this side. See, now I have something equals 0. So I had x squared plus 1 equal x plus 3. I moved the x to the other side. Excellent thought, excellent process. But I need to move the 3 to the other side as well. So now I have a quadratic equation. So I can either factor it or I can use the quadratic formula. Did anybody factor it?
I factored and I got 2 and -1.
Okay, so you got x minus 2 times x plus 1 is equal to 0. So my roots are x equals 2 and -1. And that is what goes over here. So you can't tell by my picture, but it goes from -1 to 2. Okay. This answer turns out to be 117 over 5 pi. Okay. Question.
I have a question.
Yes.
Okay, so the initial point that you picked on the x-axis to start making the circles, that's just a random number you picked between -1 and 2?
That is a random number called x. When I choose that, I just choose any x between where the ends are. And that's why the radius is a function of x. So like when we went back here and I was saying, well, if I choose, where's that x squared thing? That, yes, here. So I was saying if I was at 1, I know I'm going to be at 1. If I'm at 2, I know I'm going to be at 4. But if I'm somewhere in between, I'm just X. So the height is just whatever the function is. So down here, I did not know. That's why they're question marks. I hope y'all know those are question marks. I did not know what the limits of integration were at the time. We hadn't figured it out. But I did choose an arbitrary X, a random X. So for this next problem, we're going to choose a random Y. Okay.
Can you go over how you got 117 over 5 pi, please?
I can. Okay. So I have pi times the integral from -1 to 2. So inside here, I get x squared plus 6x plus 9. That's this piece, x plus, I don't want to use yellow. Let's use blue. This is x plus 3 squared became x squared plus 6x plus 9. I foiled it. Dizer, you with me?
Yes, I follow.
Okay. Then I'm subtracting off, well, I'm going to FOIL this. So I get x to the 4th plus 2x squared plus 1. Okay, so that is this piece. So now I'm going to simplify it. And so now simplify that for me. What does that come out to be? Anybody?
X to the 4th,
Okay, is it negative or positive?
negative,
Good, negative x to the 4th. Okay, keep going.
minus x squared,
Negative x squared minus x squared. Go ahead, keep going.
plus 6x,
Okay,
and plus 8.
plus 8. So now the last part is very simple antiderivatives. So I'm going to get negative 1/5 x to the 5th minus 1/3 x cubed plus 3x squared plus 8x, all evaluated between 0 and 1. So I get pi. When I put in 0, everything's going to drop out. So I'm going to get negative 1/5 minus 1/3 plus 3 plus 8. And if you work that out, that turns out to be 117 over 5. I will double check that. Let me just double check it. So I have negative 1/5 minus 1/3 plus 11. Oh, okay, I got a different answer. Let me see what I did. I have negative 1/5 minus
Dr.
1/3. Oh, shoot, I know what's wrong. Duh, these are wrong. This is supposed to be 2 and negative 1. I'm still doing the last problem. I'm sorry, guys. I had the limits from the last problem. This is supposed to be negative 1. These are wrong. That's why it's wrong. Okay. I was still thinking the 0, 1 problem. Okay, pi. So now I'm going to get -1/5. Let's fix this. So when I put a 2 in, I'm going to get 32/5. And then when I put a 2 in, I'm going to get 8/3. When I put a 2 in, I'm going to get 3 times 4 is 12. And when I put a 2 in, I'm going to get 16. Okay, so that's the first piece. Okay, now when I put a -1 in, I'm going to get -1 times positive -1/5 is going to give me positive 1/5. When I put a -1 in, I'm going to get 1/3. When I put -1 in, I'm going to get +3. And when I put -1 in, I'm going to get -8. There we go. And that is 117/5 pi. Okay, any questions now? Dizir, are you okay with that?
Yes, I got it.
Okay,
Do you have to do you have to plug in the final value like of the integral, or as -1 is going to 2, just plug in 2 for those values?
okay, say that again, Victor.
So in regards to the integral, when trying to just to make sure that the equation is sound, you just plug in the final value or 2 for x, so that you get 117/5.
Right, so the first piece I plugged in 2 for x, and the second piece I plugged in -1.
Oh, okay, thank you.
No problem. Okay, anyone else? Okay, next problem. Hopefully we can get this set up. Find the volume of the solid generated by revolving. Uh-oh, that's the wrong problem. Sorry, guys. I'm doing the same problem again. The region bounded by the parabola y is equal to x squared. I'll write that in. And the line y is equal to 2x. I'm going to write that in. In the first quadrant is revolved about the y-axis. To generate a solid. Find the volume of the solid. Okay, so the parabola is y is equal to x squared. And the line is y is equal to 2x. So what I want you to do is I want you to graph it. Cameras on. Okay, anybody ready to show their picture? You did it last time. I want somebody else thinking. Thank you, though. Don't stop volunteering, but I want somebody else thinking too. Anybody else have a picture? Okay, I see Gustavo's picture and it is correct. Thank you. Okay, so Gustavo's picture, if you did not see that, has a parabola. Okay, so we have y is equal to x squared. This is the first quadrant, so I'm only worried about this. And the line y is equal to 2x. So I get something that looks like this. Okay, so the blue is y is equal to 2x. And the red is y is equal to x squared. Okay, so we're revolving it around the y-axis. We're going like that. So that means you have to choose an x or a y. So somebody, when you finish getting the region that we're revolving, please let me know. Okay, I'm looking to see if anybody has their picture. Xavier, are you here?
Yes.
Okay. Anybody have a picture of it revolved around the y-axis? Kule, you look like you're done.
No, not yet.
Not yet? Okay.
I can show it when it's done. though.
What's that?
I can show mine when it's done.
Okay. Okay, so I'm getting worried because this is not a hard picture. Okay, Victor, let me see. All right, almost. I'm not too keen on that stuff at the bottom. So why do you have stuff at the bottom? Okay, so Vic, your top half of your picture looks great. You're revolving about the y-axis. So yes, when I take this thing about the y-axis, that red thing is going to go just like that. I'm going to get a red curve on the other side. And then my, and then my blue curve is going to do the same thing. So now I have a blue line coming out, going straight over just like that. So there's the region. So what you did on the, so the top part is very good. There's nothing on the bottom. Do you see this little guy right here? This little guy says only go around like that. we're not going in this direction.
Okay.
We're going around the y-axis. So your top was excellent, but you shouldn't have anything at the bottom. Okay, did you, QLA, did you get your, do you see your washer yet?
Yes, ma'am.
Okay, can I see it?
Yes, it's kind of uneven. I'm sorry.
Oh, I don't care about uneven.
But it's like the same thing. I don't know why I did it like that though.
Okay, very good. Yes, that is not exactly
Yeah.
the same thing, but it is okay. All right, anybody see their washer yet?
Oh, Dr. Lot, is it supposed to be like this? Just ignore the bottom part because I
That is
also,
what it's supposed to look like. That is what it's supposed to look like. So you choose a Y, and then you draw your circle. And I find my small radius, and my small radius is what? This is a little tricky.
2x.
So my radius is supposed to be a function of y for this problem because we're going in the y direction. So solve for x, what do you get?
Y over 2.
That's it. Okay, so that's my small radius. Because it has to be a function of y, we're in the y direction. Okay, I'm going to go back to my point. I'm going to go here and I'm going to do a big circle. I see a washer, yay. Okay, so what's its radius? Oh, we gotta stop. I see its radius. What's its radius? Help me.
Y.
This radius has to be in terms of y, so fix that function.
Square root of y.
Okay, good. X is equal to the square root of y. Got to fix that function. So your big radius, y, is the square root of y. And so now you can finish it. So I get the volume is the integral. You have to find what C and D are of pi. The big radius is the square root of y squared minus the little radius is y over 2 squared dy. Okay, set them equal to find your limits of integration. And you're going from the y values now. So you start, I can give you a hint. The first one is 0. And then you got to find out what this value is. So you got to find that point. This answer turns out to be 8 pi over 3. And is today Friday Eve?
Yes.
Yes.
Yes. Okay.